Okay, so this lecture is about the design of a telescopic cascode differential amplifier that you had to do in assignment 3. So this was a circuit we are going to design, and these are the specifications. The differential mode gain had to be greater than or equal to 1000. The common mode gain less than or equal to 25 dB, which is 18. The output voltage, DC voltage range had to be 2.6 volts to 2.3 volts. It could of course be greater, but it cannot be lesser. So the maximum voltage has to be at least 2.6. The minimum has to be at least 2.3. So minimum can be less, maximum can be greater. The DC power consumption is less than or equal to a value that was given individually to you, and the minus 3 dB frequency had to be maximized with a CL of 10 picofarad. All right. Now this is a very unique design because of the constraint of the VO max being 2.6 volts. It is stringent because it allows for only 0.4 volts across the top two transistors in the stack, and because this voltage is small, this voltage allowed is small, it will affect the voltage gain. Why? Because as you may recall from assignment 1, the data of assignment 1, the smaller the drain source voltage across a transistor, the larger is its lambda, and therefore the smaller is its gain. Therefore one has to choose the values carefully. Okay, so with this we begin the design with this recognition of to meet 2.6 volts. So other than that, we as usual begin the design by considering the differential mode gain. The expression for the gain of course is this GM1 GM3 RO3 RO1, that is a resistance looking down from the output, in parallel with GM5 RO5 RO7. This is in the differential mode, so the source node of M1 M2 will be at virtual ground, and this has to be greater than 1000. Alright, now it is easier to begin this design by first considering a single input telescopic cascode and then taking these values to the differential cascode. So we start with the single input telescopic cascode, for which the magnitude of the voltage gain, I am calling it AT, is this, which is the same as this except for the factor of 2 which comes on a differential amplifier. So this has to be greater than 1000. So if you take the 2 out to the other side, then the gain of the single input telescopic cascode has to be greater than or equal to 2000. Now let us write out all of these as we usually do. So GM1 is 2ID over VO1, similarly GM3, RO, R1, etc. etc. So there are 2 IDs in the numerator, 2 IDs in the denominator, so they cancel, and the factor of 2 comes out, so we get a 4 here, 4 by VOV1, VOV3 lambdas, a lot of lambdas, and these two are parallel resistances, so the conductances add. So this is the expression we get for the voltage gain of the single input telescopic cascode. Now of course our purpose is to kind of get a sense of what values we should start our design with. And there are too many parameters here, so we'll simplify this further. So we say, well, let the lengths of the NMOSs be equal, the M1, M2, M3, M4, and therefore their lambdas are equal, and similarly let the lengths of the PMOSs be equal. So we'll get lambda n squared and lambda p squared, and we want a large gain, so we want VOVs to be small and of course lambdas to be small. Let us make all VOVs 0.1 volt. Alright, let us begin with that. And so we substitute 0.1 here, and so 0.1 times 0.1 is 0.01, so this becomes 400 1 by lambda n squared plus lambda p squared greater than or equal to 1000. So we get an expression for lambda n squared plus lambda p squared must be less than or equal to 0.2. So we have to choose lambda and lambda p to meet this above condition. Now I was doing this, I thought that this is even simpler to do if we start with the common source stage, which is a single PMOS, single NMOS rather than two PMOS, two NMOS. Remember that the gain, so let's go back here. So this is GMRO squared. The gain of a common source is GMRO. So if we design the common source stage with a GMRO and get all the lengths and etc., then the telescopic cascode will simply be the square of that circuit. The factor of 2 here and there, but that will come about by itself. So we say let us go back to an even simpler circuit, which is a common source stage. And just to get a sense of the values, let us for the moment assume that lambda n is lambda p are equal. And so our condition from here, lambda n squared plus lambda p squared, so we say that is equal to 2 lambda squared should be less than or equal to 0.2. So lambda squared less than or equal to 0.1. So lambda square root of 0.1 is about 0.31. Now for the common source amp, the gain is the A common source. I'm just writing the magnitude again. There is of course a negative sign, but it doesn't matter here. 2 over VOV lambda plus lambda p. So if the lambdas are equal to lambda, all this we've said VOV is 0.1 and we want lambda to be 0.31. So the gain of our common source amplifier needs to be 33. So 33 square is 1000, which is what eventually we want. So we start by designing a common source amplifier with a gain of around 33. And in order to do that, so we say, okay, we want this to be 33. We make VOV 0.1 okay, so I'm getting lambda n plus lambda t equal to 2 divided by VOV into 33 equal to 0.6. So if we look at that, if you go back and look at the data of assignment 1, we want to choose lengths for the NMOS and PMOS so that the lambdas add up to 0.6. Alright. Now again, let us recall our condition that the VDS of the PMOS is only about 0.2 volts, by the way. So maybe I should go back. Let me go back here because this is, here. So we say that the DC drop across M6, M8 together is 0.4 volts because VO max is 2.6. So 3 to 2.6 is 0.4. So across each PMOS, the voltage, DC voltage drop can be only 0.2 volts. And therefore, when we design the common source, the voltage drop across the PMOS has to be only 0.2 volts. All right. So, and because it is 0.2, its lambda will be large. So I have chosen, and of course this is up to you, there are various combinations possible, and as I have said before many times, designs are never unique. This is one example of how to go about doing the design. If you do it yourself, perhaps you will come up with a different set of numbers, but here is a representative design. So I have chosen both to be 0.36, the lengths of NMOS and PMOS, for which for the NMOS, the lambda is 0.2 at a VDS of 1.5. Actually, VDS is 2.8 for the NMOS because the VDS of PMOS is 0.2. The total is 3. But because the assignment 1 table had only up to 1.5, I have taken the value of 1.5. It really doesn't matter as we'll see because these are just initial starting values. We are going to change them all over the place. But this lambda is 0.2, and for the PMOS at VDS of 0.2 volts, the lambda is about 0.4. In fact, actually this is also not there in the table. I had to find it because we did not do in our table drain source voltage of 0.2 volts. And I have also written the threshold voltages for these lengths for the NMOS and PMOS, because these will determine our gate voltages. The gate voltage is the threshold plus the overdrive or minus the overdrive. So for the PMOS, the gate voltage is the VDD minus the threshold minus overdrive, so 2.36 volts. And I am starting with the widths of WP equal to 3WN, that is just roughly based on the mu Cox ratios. And I am starting with a W of 100 ln. As we will see after a few slides, this the W we choose is variable, and it we'll see. I'll say what I have to say later. But anyway, these are starting values. So we say VGP is 2.36 volts. The lengths are 0.36 and 0.36. Okay. Now we note again, because this is important, that we want to obtain a gain of 33 when the output DC output voltage is 2.8 volts. This is kind of our DC quiescent point. Now our model, as we see, being very approximate, our hand calculation model is very different from the BSIM3 model that SPICE uses. So our initially chosen numbers will not give us the gain most likely, and will vary various things to get the gain spec. And the not meeting the gain spec, of course, means that the gain will be smaller than what we desire, and the way we increase the gain is by increasing Ln and Lp. Now as we change Ln and Lp, we'll have to remember that with Ln and Lp changing, their VTs will change. And as VTs change, we'll have to make sure that the overdrive voltage remains at least 0.1 volt for each transistor. For the PMOS, to make sure that VOV stays 0.1, we'll change the gate voltage. Alright? Because the gate voltage has to meet this VG equal to VDD minus VTP minus 0.1 volt. For the NMOS, we'll change its widths. I'll show how this happens. Okay, so with this, let me open a SPICE file. So with these initial numbers, let us start our design. Alright, so this is the initial. So these are LP and LN are 0.36, WP is 300 LP, W1 is 100 LN, and VGP is 2.36 volts. Alright, the output terminal is, I have called it out. Now what we want to do is we'll sweep the input voltage. Input is the gate of the M1. We'll sweep it and watch the output. I think it's already run, but anyway, let's run it again. And then we plot the output voltage, and along with the output voltage, let us plot something else so that we can plot the gain. So I'll make this minus dV out, minus dV out. All right. Okay. So this is the output voltage. This is the blue is that so-called transfer characteristic, which is the output voltage versus the input voltage. And as we can see, for very low input gate voltages at the NMOS, the output is near to 3 volts, because the PMOS is in triode, because the NMOS current is very small at small NMOS gate voltages, and the PMOS saturation current is large, so PMOS goes into triode. Then as the NMOS gate voltage increases, at some point the PMOS goes into triode and the voltage drops, and here in this range both the transistors are in saturation, and at high gate voltages at the NMOS, the NMOS goes into triode and the gain becomes small and the output voltage becomes close to ground, because the NMOS drain source voltage is small. The red is the gain. Now, as I said, we need to look at the gain when the output is 2.8 volts. All right. So let me see. So this is 2.8 volts. Okay, here. So the output voltage has to be 2.8 volts. At that point, we want to see how much the gain is, and we want to make this gain greater than 33. So this is V out. If I click on the gain, and tells me at that same point what the gain is. So at the same input voltage, the gain is 21. All right, now we want 33. So we have to increase the lengths. So this now is a bit of a trial and error. So what I'm going to do is I'm going to skip a few steps because I kind of know the answer. But the thing to do is, as we said, at this voltage, the PMOS has a very large lambda because the drain source voltage across the PMOS is small. Therefore, the first thing to do is to reduce the lambda of the PMOS, because if the PMOS lambda is large, even if the NMOS lambda is made very small, the PMOS lambda will dominate and it will not let the gain go up. Alright, so I'm going to make this 1 micron. Alright, now as I make this 1 micron, the threshold voltage of the PMOS will change. So let me look up the threshold voltage. Oops, sorry, not this one. I have it open here. So this is the table from assignment 1. So at a threshold, so this is a PMOS threshold voltage. So at a threshold at a length of 1, the PMOS threshold voltage is 0.51. This I have written minus VTP is 0.51. If this is 0.51, then okay, let us see here. So let us go back here. So this 0.54 becomes 0.51. So I need this to be 2.39. All right, 3 minus 0.51 minus 0.1 is 2.39. And I want to make VOV as small as possible so that the gain is as large as possible. So I'll make this 2.39. This is actually not required. The VOV of the PMOS actually can be larger, but as I said again, this is just one possible way of designing. Alright, so I have made the length larger. Now I'm going to run this again and see what the gain comes out to be, and then change again the lengths. Alright, so let us see at this. So this is let me see. So the output voltage has to be at 2.8 volts. So I have to get the voltage at which this is 2.8, the output. So around here, 544.1 millivolt is the input. At this voltage, the gain, so I click here, is 34. 34 sounds about right. Okay, but there is a, alright, so the gain is met, but now we have to make sure that the NMOS gate voltage, so what is the NMOS gate voltage? 0.544 millivolts. Now let us see if this 0.544 gives an overdrive of 0.1 volt. So at a length of 0.36, what is the NMOS? The NMOS threshold voltage is 0.508, which means that the gate voltage has to be at least 0.608, right? 0.5 plus 0.1. So this is too small, so we can't afford to have such a small overdrive voltage. So we need to increase the DC gate voltage or the DC gate bias of the NMOS. Currently it is 0.544. We need to make it 0.60 whatever. What was it? 0.608. So we want to increase the gate voltage of of the NMOS. The PMOS is acting as a current source, so it is applying a constant current. We want to increase the gate voltage of the NMOS, so we must reduce its width so that the same current flows. Alright, so I'm going to reduce the width of the NMOS, and because okay, I think it was, now I don't remember, because one has to play around. Okay, let me cheat and look up, okay, because you can do this yourself. 58 is what I want, so I'm going to make this 58. It is trial and error, but in order to save time here, I am putting the value that I know will give me the right. Okay, so let us see again. This one 2.8. I want this to be 2.8. Okay, 579.6 millivolts. Still not high enough. But let us see the gain actually. Okay, so let us see the gain. Now what is the gain here? The gain is become 30. It is less, we need at least 33. So again one can change either LP or LN. By the way, so the VOV is not met yet, but I'm working on the gain first and I'll come back to the VOV. One can do it either way. Ultimately both have to be met. And again one can change either LP or LN. I changed LN to 1 because that is it worked for me. So I'm going to make this 1 and run it again and see if it meets the gain. All right. Okay, let us see. Now this one. So this is the gain. Okay, how much is the gain? The gain is 36. So the gain is met. Now let us see at 1 micron ln what is the threshold voltage and whether that is okay. So at 1 micron the threshold voltage of the NMOS is 0.43. So I need 0.53. Alright. So I need 0.53, where it's 0.534, but that 4 millivolt will ignore. So I have 0.53 here, which is adequate, right? 0.43 is the threshold voltage. So the gate voltage of the NMOS has to be 0.53, which it is. And I'm getting a gain of 36 at an output voltage of 2.8 volts. Alright, so this common source amplifier is meeting all the requirements that I am looking for. So I say, okay, these are my designed values. LPLN is 1 micron, W1 is 58 times Ln, W3 is 300, and VGP is 2.39 volts. With these values, now we go back to the single input telescopic cascode. Alright, so you can use the same values and go design the single input telescopic cascode. So here is the single input telescopic cascode. So we say the PMOSs will keep the lengths and the widths as they are. The 2.39 is the top PMOS voltage because that is the one acting as a current source. So making this as 2.39 will give us the same current here as was flowing in the common source amplifier. The NMOS lengths and widths also will keep as they were in the common source amplifier. There are two additional voltages that need to be determined. So let us talk about those. So VG5 has to be such that M7 has a 0.2 volt drop across it, right? We want a total of 0.4 across two transistors. So we want 0.2 across M7. So this node has to be at 3 minus 0.2 at 2.8 volts. And the gate source voltage of the PMOS will be the same as the gate source voltage of M7. Alright. And so we say whatever the gate voltage of M7 is, we'll subtract 0.28 for the 0.2 across the M7, and therefore we get a gate voltage of 2.19 for M5. The gate voltage of M3 is actually not of great significance If we were to follow the same logic here, then this is at 0.53, it is here, right? So this is 0.53 volts. We want a 0.2 across M1, and so this has to be 0.73. But there is no constraint on making VG3 higher, all right? We cannot make VG5 lower because we need VO max to be 2.6, and if we make VG5 lower, VO max will go down. VO min is like whatever, 2.3 volts, right? So which means that VG3 can be very high, and the higher VG3 is, the higher VD1 is, and the higher the lambda of M1 will be. So I have just taken some in between value. This can go up to 2.2, 2.3 also. It could go down to 0.7 also. The whole range available to VG3. We don't want to make it low because the lambda of M1 will be small. We could make it higher. I have left that to you as homework or whatever to do, try it on your own. But I have put it 1.5. So with these values, we want VO over Vin to be 2000 for this circuit. All right, at VO equal to 2.6 volts. All right, so let us put these values in a telescopic, single input telescopic cascode and simulate it. All right, so let me close this, open this one, which I have already put in the values. So VG3 is 1.5, VG5 is 2.19, VG7 is 2.39. The lengths are the same, 58 and 300 from here, 358. Lengths 1 micron, widths these. Okay, let's make it visible. And we'll sweep the DC gate voltage to arrive at the exact gate voltage we need to make sure that the output voltage is 2.6 volts. All right, and so this is a circuit. I'm not, this is the single input telescopic cascode. The M1 is the input transistor, G1 is the gate of M1, and the output is taken at the output terminal out. All right, so this I'm finished with, so I'll close this and we'll run this one. So let us run, and now let us plot again V out and another voltage which we will make. All right, so this range is very small. All right, so V out is dropping sharply, which is where we want to place the transistor. Let me make this the derivative of V out. Okay. Now actually I wanted to make a comment earlier, but let me make it now. Okay, so what we want again is that we want to bias this at now a V out of 2.6 volts because now it's a cascode. So we want the output voltage to be at 2.6 volts, which is here. All right, and so the input voltage is something 545 millivolts. Now I want to make a comment that, as you can see, look at the gain profile, right? The gain is highest somewhere here. Okay, and this is an important thing to recognize and observe. The gain of this telescopic cascode reaches its maximum somewhere here when the input voltage is somewhere here and the output voltage is somewhere around 1.5, 1.6. All right. Now let us think about it. Why does the gain reach the highest value somewhere in the middle of the output voltage range? The answer is, as I observed earlier, the lambdas of the NMOS and the PMOS are functions of the drain source voltage. Now around 1.5, the drain source voltage of the PMOS, the two PMOS stack is 1.5. The drain source voltage of the NMOS stack is 1.5, and so the drain source voltage across each transistor is about the largest possible. And because the drain source voltage is the largest possible, the lambda is the smallest possible, and therefore the gain is the highest possible. Alright, here when the output voltage is 2.6, the drain source voltage across each of the PMOS is only 0.2 volts, and because it is small, its lambdas are large, and therefore the gain is smaller. Alright, but we are constrained to design the circuit with an output voltage up to 2.6 volts, because we are going to use this output to drive the gate of the PMOS of the common source stage, which you will connect in the next assignment. Alright, but now okay, so with all this, let us look at what is the gain at 2. So this is the output is 2.6 volts. What is the gain? We want 2000, right? Okay, so here the gain is 2148, which is good. So we are meeting the gain criterion even at 2.6 volt output voltage. So this is now working fine. The telescopic cascode is giving, the single input telescopic cascode is giving us the gain that we wanted at the output voltage that we wanted. So with this now we say, okay, now we've kind of finished our next step. Now let us go design the complete differential cascode. Alright, so this we finished. Now let us do the complete differential cascode. So we'll use the same numbers for M1, M2, M3, M4 up to M7, M8. The same lengths, the same widths, the same gate voltages at M3, M5, M7. Alright. The new addition is M9. So we need to determine the gate voltage as well as the length and width of M9, so that this will work with everything in saturation. So we say, well, to begin with, all the lengths are 1 micron. So let us make L9 also 1 micron. Let us make the width of M9 twice the width of M1, because M9 carries twice the current as M1. So twice of W1 is 116 of Ln. Alright. And then, so that width and lengths are determined, how much VG9 to put. VG9 requires a very, very accurate number. We shall see. So with this, let us simulate. Okay, so these are the steps we'll follow. So we'll determine VG9 by doing a SPICE DC sweep of VG9. Once we fix VG9, then we'll check if the differential mode gain is greater than 1000. If it is, well and good. If not, we'll have to change again some length somewhere, or in fact only the length will help. So if needed, we'll have to change the length. Otherwise, if this is met, then we'll have to look at the common mode gain, because there is a requirement. The specification is that the common mode gain has to be less than 17. So if the common mode gain turns out to be greater than 17, we'll increase the length and width of M9. Alright, and so actually I've written the answer already, but that's okay. Let us go through this. So what we do is, so let me close this and let me open the full differential cascode circuit. And with the same numbers we'll put. So okay, so this will come back. So let me see. Okay, so VG3, VG5, VG7 are the same as the single input cascode. The length is 1 micron for everything. The widths are 58 and 300. 58 and 300. The width of M9 is twice of 58, which is 116. Alright, and now what we'll do is we'll do a DC sweep of VG9 to first determine VG9. So let me make this 0.52 to 0.55 and we'll run. One more thing. the DC at the input voltages, that we need to talk about this. Let's go back. So what value of DC voltage do we put at the inputs of M1 and M2? When we did the single, this one, it was some value, actually I have forgotten, I have not written it down because it was not important. It is 0.54, right? So this was 0.54 for the single input telescopic cascode. Now of course there is a transistor below, so if we keep this as 0.54, then obviously with this also around the same voltage, the M9 will be in triode. Alright, if this is 0.54, M9 will go into triode. So we have to increase the DC voltage at the gates of M1, M2 to make sure that M9 stays in saturation. That is one consideration. So there is a minimum value at the gate of M1, M2 that is required to make sure that M9 is in saturation. Above that, when we discussed differential amplifiers, we saw that the DC common mode gate voltage has a range over which all transistors stay in saturation. So there is a minimum and then there is a maximum. That range, if you recall, is called the input common mode range, ICMR. So there is a range for which this circuit will work. We just have to make sure that these voltages are within that range. We can put any value you want within that range. It is up to you. Alright. I have taken 1 volt because it's just a nice clean simple number. But in fact you should find the ICMR for this circuit. I have not found here. But you know how to find. You go back and look at the differential amplifier lectures. You can find the ICMR and then you make sure that these two voltages are within that range. Alright, so with that, so I have put 1 volt for V in 1 and V in 2, and then with that we find the VG9. So okay, so I'm closing this and now let us run. So I'm sweeping VG9. What happened? Okay, there's an AC analysis, don't want AC. Okay, so let us run and let us plot VG9. I'm sorry, V out and something else. Okay, so V out I've called VO now. Okay, so actually this is far too much to the side. So let me change these voltages, 5, 4, 5 to maybe 5, 5, 5. Okay. Alright, so what this is telling us is that as VG9 is varied in this range when the output voltage drops drastically is when all transistors are in saturation. So we have to apply a gate voltage at M9 in this range. In fact, we want to bias the output voltage at 2.6 volts, right? So we'll find the gate voltage at M9 required to make the output 2.6 volts. All right, so here, maybe here, 549064, 549064, right? That is this voltage. So at this voltage, the output is basically 2.6 volts. So, alright, so this becomes our DC operating point for the circuit. With the input DC voltage is a 1 volt, VG9 being this number. So this number is very critical. A small change is this number, as you can see, would change the output voltage very sharply, and therefore we have to define this voltage very accurately. By the way, I have said this once before, maybe such accurate voltages are of course impossible to generate in real life, and therefore to obtain an exact output DC voltage of 2.6 volts in such a circuit is impossible. And we have seen this from another perspective, that the output node of the telescopic cascode is a high impedance node, and therefore fixing or determining its output voltage exactly is an impossible thing. We are cheating here by fixing it. The way this is done in actual real life op amps is by something called as common mode feedback, which we will study later on in chapter 9. By the end of chapter 9, we will learn how to fix this voltage to be exactly 2.6 or 2.5 or 2.4, whatever voltage we need. But all these are relevant. All this design is relevant even with common mode feedback. Okay, so this is the value we use. So now with this gate voltage at M9, we have a full differential telescopic cascode with all DC voltages defined, all lengths and widths defined. Now let us see if it gives us the gain we desire. So to find the gain we desire, there are two ways we can do it actually. We can either do a DC sweep or we can do an AC. Let me do a DC first. So I am going to vary V in 1 of the input voltages and watch the output. Alright, so let us, am I doing it correctly? Yeah, okay. So let's just run this. Alright, so this is the output voltage as the input voltage varies, not VG9 anymore, but the input voltage varies. And we want the output to be at 2.6 volts. So it is about 2.6 volts. The input, okay, so that's another thing. We want to measure or look at the gain when the input, so I am varying the input voltage from 0.99 to 1.01, a very small range. Why? Because this voltage gain is very high. So the output changes from high to low over a very small range of the input voltage. And I want to look at the gain of this, the differential mode gain of this circuit, when both the inputs are 1 volt. I am fixing V in 2 to be 1 volt. I am varying V in 1, but I want to find the gain exactly when the input is 1 volt, 1000 millivolts. So at that volt, and I am getting the output as 2.6, as of course that was designed because of this VG9. So let us find the gain. What is the gain? It is 1061. So it is greater than 1000, which is what we wanted, and this is as it should be, because this is exactly the single input telescopic cascode circuit. Because for these numbers, for a differential mode input, the source of M1 M2 is virtual ground, and this should give exactly the same gain as the single input telescopic cascode circuit. Now let us check this by doing an AC simulation. So instead of DC, I'll do an AC. For doing AC, I'm applying an AC minus 0.5 at V in 1 and AC plus 0.5 at V in 2. Now why minus 0.5 and plus 0.5? So these are the AC inputs. To find the differential mode gain, on paper we apply a plus Vd by 2 and a minus Vd by 2 at the inputs, and then the differential mode gain is defined as VO over VD. Now in simulation, I am saying this is basically minus half and plus half, so that the differential mode input applied is plus half minus minus half, which is 1. So the input differential mode voltage applied is 1 volt. And if we simulate this, then the output voltage for an input of 1 volt will directly give the voltage gain of the circuit. This is why we apply plus 0.5 and minus 0.5. For example, if we apply 1 and 1 here, then the differential mode input will be, 1 and minus 1. If you apply 1 and minus 1, then the differential mode input will be 2, and what we'll see, the output will be twice the voltage gain. Okay. Alright, so let us run this. Alright, so the blue is the output, and the output is giving us 60 dB, which is what we wanted. We wanted the gain to be at least 60 dB. So it is meeting. Okay, so our circuit is meeting the differential mode gain criterion, which is good. Now we must look at the common mode gain. So let me, so to find, okay, so let us find the common mode gain. One could do it here. Okay, let us do it here. So how do we find the common mode gain? We apply the same input of 1 volt at the both the inputs, 1 volt, 1 volt, common mode AC input, find the output. So we run this, and the DC, how much is this? So this is 25.5 dB. We have to get less than 25, so this is slightly higher. We have to do something to reduce this gain. All right, so let me go back. I personally prefer doing DC. So let me do DC. So maybe 0.95, 99 seems to 105. Okay. So I want to do a common mode simulation, DC sweep. So what I want to do is, I want to apply the same input at both the same voltage at both the inputs, V in 1 and V in 2. So I'll short the gates of M1 and M2 and apply the voltage V in 1 at both the inputs, which is, and I'm varying that V in 1. And then let us run this. So, okay. So the blue is the output voltage for a common mode DC input, or the 1.05 is not enough. Let me make it 1.1 so we can see the whole range. All right. Okay. All right. So this is the, here is the reason why it is better to look at the DC. Okay. So this is the output voltage as a function of the common mode input voltage. And it is of course at the same shape, but the slope of course is much smaller than the differential mode case. And as you can see, the gain is about, it is varying from about 24 to about 40. All right. Now what we saw in the AC when we applied both 1 was the voltage gain when the output was 2.8 volts. I'm sorry, 2.6 volts, somewhere here, or at this input voltage. All right, 1 volt. So 1 volt when the DC inputs were 1 volt is what we saw. Let me be precise here. So when both the inputs were 1 volt, the common mode gain was 26. I'm sorry. No, the gain is this one. The gain is 18.9, all right, which was 25.25 dB or whatever. We want the gain to be less than 17. But here is the thing. We want the common mode gain to be less than 17, not just at this point. We want the common mode gain at any common mode input to be less than 17. So the AC gave us only this one point of information. The DC sweep gives us the common mode voltage gain over the entire range of common mode inputs possible. All right, because why is this important? Because when we actually use this op amp in an actual circuit, in an actual application, the common mode input would vary. It won't be fixed exactly at 1 volt. It can be 1, it can be 2, 1.5, whatever. And therefore, we have to find the full possible values of the common mode gain and then make sure that at any common mode input, the gain is less than 17. All right, so now this is 40, so we need to bring down this 40 to 17 or below 17. So the way we do this is to increase the length of M9. So where is M9? Here. So and we'll keep the W by L the same and we increase. And as I said, I'm going to shortcut this, and I figured that at 3 times the length. So I make the length 3 times and I make the width also 3 times so that the W by L remains unchanged. Let's see what happens. But okay, so but as soon as we do this, we change something in M9. We have to go back to VG9 and adjust VG9 so that everything remains in saturation, because VG9 being so, everything being so sensitive to VG9, we have to sweep VG9 to make sure that we choose the right VG9 to keep everything in saturation. Alright, so I need to increase this range. So let's make it 0.52, maybe 1 micron too little. So okay, so it is here. Alright, so now we need to change VG9 so that with this new value of, VO, with these new values of LN9 and WN9, we want the output voltage to be 2.6 volts. We want to adjust the VG9 so that the output is 2.6. So that is 52255. So let's make it 52255. But I want to make sure now that VG9 has an overdrive of greater than 0.1 volt. So now the length is 3 micron, right? Ln is 1, Ln9. Let's close this. Ln9 is 3 times length, so 3 micron. So what is the threshold voltage of an NMOS at 3 micron? Okay, I don't have it here. I mean, we didn't do this in the first assignment, but it's clearly between 0.41 and 4.4 volts. So anything gate voltage above 0.51 will ensure that M9 has an overdrive of 0.1 volt. All right, so 0.51, this is 0.52, so we are safe. All right, so this is a good enough gate VG9. With this, let us find the common mode gain. So we'll again simulate with a common mode voltage applied. So G1, G2 are shorted, and we'll sweep Vin1 and find the output voltage and the gain. All right, so let us see this. Maybe we need to apply a higher range to make sure that we see the highest. All right, so this is the output voltage, red is the gain. The highest gain we are getting is less than 16. All right, so now we have met all the, we have met the differential mode gain and the common mode gain at an output DC voltage of 2.6 volts. All right, and okay, let's do one more simulation just to complete this. So again, we'll apply a differential mode input. Let's do a sweep of with a differential input. So we'll apply an input only at the one of the inputs. The other input is constant at 1. Okay, just check and also make one more observation. So okay, so this is at 2.6 volts. 2.6 volts. The input is exactly 1 volt. The gain is just 1000. All right, so it is met. The output voltage range, the swing, is from 2.6 to almost 1 volt. All right, so it is greater than we needed 2.6 to 2.3. This is greater, not a problem at all. Greater, nobody is going to say this is not right. Okay, so we've met all the DC criteria for the circuit. Now let us think about the 3 dB frequency. All right, so this is designed. These are the L9 is 3 micrometer, and now let us think about the minus 3 dB frequency. The problem said, or the assignment said, maximize the minus 3 dB frequency, and the expression for the minus 3 dB frequency was given 1 by CLR out. CL was given 10 picofarad. So to make an omega minus 3 dB as high as possible, we have to make R out as small as possible. R out, as we know, for a telescopic cascode is this, and we write out in terms of ID, lambda, all that. And we can write it as, so there is one ID in the numerator, 2 in the denominator. So one ID comes out, And you say get 2 over ID, VOV3 lambda, VOV5 lambda. Now VOVs and lambdas were determined by our grain criteria. Alright, so we made these 0.1, 0.1 lambdas we chose from our lengths. So these we can't change now. Alright, so if I want to increase omega 3 dB to reduce R out, all we can do is make ID as high as possible. Alright, so the way to design this now is to make ID as high as possible. How do we make ID as high as possible? So you were given a power, let me open the assignment statement. So you are given a power number, so each one had a unique power number, and the power number of course directly tells you the current that can be allowed, right? So this power is basically 3 volts times the current flowing. So let me take a nice number. So let's say it is 1200 microwatts is the power given to you. Then 1200 microwatts is equal to 3 volts times the current supplied by the 3 volts. So that current is 400 microamps. So each branch can be carrying 200 microamps, no higher, according to this power specification. So you want to make sure when you do this design that if your current can be 200 microamps in each branch, then you choose that current to be 200 microamps. If it is lower, your omega 3 dB will be lower. Alright, so that is our next step of the design, is to make sure that the current as determined from the power is exactly what you can get and what you are the highest you can apply. Alright, now to do that, let us look at this for a minute. So these are the numbers we have designed currently in the last so many slides. So the gate voltages are these, the widths are these, and the lengths are these. All right. For these values, the current turns out to be 124 microamps. All right. So in fact, maybe I should show that here. So let us plot the current also. Any current. Let's plot ID1. Okay, so the current also has to be found exactly at this DC bias point. So I click on this and it gives me the current. So the current is 123.8 microamps. So basically 124 microamps. All right, that is the current flowing. Oops, sorry, what happened? Everything is closed. I wanted to be here. 124 microamps. Now, here is the property of this circuit and most amplifier circuits. If I want to change this ID, so as I said, let's say the power given to you was, whatever was that number, what did I keep forgetting, 1200, so 400, so 200 microamps, all right. So I am getting 124 microamps. I want to change this current to 200 microamps so that I get the highest possible omega 3 dB for the power number given to me. So how do I do that? I have 124 micro, I want to change it to 200. Now it is a property of these circuits that if I keep the ratio of these widths unchanged and change all the widths by the same factor. So let us say I was to double all the widths, all right, widths. Voltage is same, length same, change the widths. If I double all these widths, then the current will double. If I make this 3 times, the current will become 3 times. All right, this is a property of these circuits. Why? Because the current goes linearly with the width, right? ID is equal to mu1 Cox W by L VOV squared. If you keep everything else the same, change W only, scale the W, the current scales according to W. So if we keep these widths the not change ratios of which, this is 300, this is 58, this is 348, don't change these, just multiply this by the same factor, then the current will change by that same factor. Razavi calls this linear scaling. Right? This is linear scaling is a property of such amplifier circuits. So all you have to do is, suppose I want 200 microamps from 125 microamps. I multiply all the widths by the factor 200 by 124 to be precise. Right? So if I multiply all the widths by 200 divided by 124, then your current will become 200 microamps. And similarly for any other current. And therefore, for every current, you'll get a different set of widths and a different omega minus 3 dB, because the omega minus 3 dB will change with the drain current. Alright. Now here is another thing. All these designs, so each one of you individually, whatever power you are given, you could use these same numbers for the gate voltages and the lengths. Alright, all you can change is the widths. That is one way of doing it. But as I said, if you sit and start yourself with the original 0.36 micrometer for the NMOS and the PMOS, and then you tweak yourself, I am sure you will come up with many different set of lengths for which you will meet the specifications given. And I think that you should do at least once, maybe even twice. Alright, so I am leaving that to you. This is one possible way of designing the circuit. Okay, one last thing. I did not spend much time on VG3. As I said, VG3 has a whole range. I have made it 1.5 volts. Over a whole range, all other specifications will be met. So I would like you to sit, once you finish designing, so what I am suggesting is you design the circuit yourself for your given set of, your given power consumption number, but design your own lengths for the NMOSes, PMOSes as well as M9. Come to this point. Once you design, just change the widths. Initially, don't worry about the widths. Do as I have done. Once you arrive at this point, then you scale the widths to meet your current number. Then you will have a final circuit that meets all the specifications. Then you vary VG3 and you do plot DC transfer characteristics, output versus input, and watch the effect of VG3 and make some observations. Alright, this is useful, but as I said, it is not critical, so I am not doing it here. Alright, so that is the end of this lecture. Next lecture, we will continue with our higher gain op amp configuration.